today's notes are on page 12, and we'll cover conditional probability. So I'm going to read through the definitions, and at any point, we'd like to pause when I'm done. If you haven't got everything written down, then please do so. So conditional probability is the probability of an event will occur given that an event has already occurred. So there's two different conditional probabilities, independent and dependent. Independent is when the event that has already occurred does not affect the probability of the new event. The formula for that is the probability of A given, this is our symbol for given, B. That's just going to be equal to probability of A because the B event doesn't matter, doesn't affect what's happening. And we could also write it as the probability of B given A, and that's just going to be equal to the probability of B, again because that A, whatever's happening there, doesn't matter. So you would be just finding essentially the probability of the first thing given to you. Now when it's dependent, we have a little bit more to do. When the event that has already occurred does affect the probability of the new event, it's a dependent conditional probability. So we would have the probability of A given B. Now this is when it will affect it. This is a symbol from before. This symbol stands for and. So that is your indication that we would be like multiplying here. So this time we're going to take the probability of A and B, so the overlap at intersection, and then divide out by the probability of B. We could also write it as the probability of B given A. And it's the same formula except for you would divide out by the probability of A this time. So notice the location of what you're dividing out. The second thing that you get after that given bar is what's going underneath that denominator. The second thing you get after that given bar is what's going underneath the denominator. That is something that you can count on to always be true, so it kind of visually even looks like something that you would be doing. But remember, we're going to find the and, the intersection probability, and then divide by all the same digits. Alright, so independent. What is the probability of a red cube and a white cube, both numbered 1 through 6, both landing on 3, if you know that the white cube landed on 3? Well, if I'm rolling these cubes separately, they have no effect on each other. It's not like the red cube knows what the white cube is on. So essentially, I am just finding the probability of a red 3. Well, on my 6-sided die, that's only 1 square. What is the probability of both cubes landing on an odd number if you know that the white cube landed on 3? So the white cube already successfully did this. Again, has no effect on my red cube. So essentially, I just want to know the probability of red being odd. Well, of my 6 numbers, there are 3 total odd numbers. So that's 1 time. What is the probability of a penny, dime, and quarter all landing on tails if you know the quarter and the penny landed on tails? Well, on this one, we know that the quarter and the penny are on tails. The dime does not know, so essentially we only care about the dime. So we want the probability that your dime is tails. Well, of your 2 sides of the coin, only 1 is tails. 1 half probability. What is the probability of all 3 coins landing on tails if all you know is that the quarter landed on tails? We already know that the quarter is on tails, so we need to figure out the penny and the dime. So we want the probability that the penny is tails and the probability that the dime is tails. Well, that's the probability of penny is tails, so that's 1 half. And so times the probability of the dime is tails, so 1 half is 1/4. We don't do independent as often, we really focus on dependent, so let's look into that. Students are responding to a poll. We're asked whether they were for, against, or had no opinion about a proposal to increase funding for the school supply program. So again, this bottom number down here is the total number of people that were given the survey. So 100 people were given the survey. And it's broken down into all of the different categories. So when you're given a table like this, you really want to just hone in on what we're specifically talking about. So we have, what is the probability that a randomly selected student would be for the proposal given that the student was a girl? So if I wanted to write this in conditional probability format, probability for, well, 4 is letter F, given, so that's the bar, the student was a girl, and girl is letter G. So remember, if I want to rewrite my formula, that's the probability of F and G divided by 14 seconds, so the probability of G. So if I'm looking at that, well, this is like the compound probability. Because remember, this means and just means your intersection. So I want to look for the intersection of F and G. So F and G and G. Now here's the problem. I'm only looking at it given they're a girl. So really, essentially, all I care about is the girl row. I don't care about the boys that were for it or the total out for it because I know I'm dealing with a girl. So I can get rid of, disregard this and this, and really all I'm looking at is that overlap of 4 and girls out of my total girls that were asked because I know it's a girl. So 10 is that overlap in 45 total girls were asked. So we're reducing that's 2 out of that. Okay, let's look at that one. What is the probability that a randomly selected student would be a boy given that they are for the proposal? So probability boy given 4. Well, I'm going to go to just my 4. I only care about the ones that were 4 because I know that I'm only looking at that column to figure out who are my boys. So always start with your given. I'm given that there are 4. How many of those are also boys? Well, my overlap is right there. So 40 out of my 50, 40 boys, given they were 4. And I'm reducing 4 out of that. All right, let's look at our last one. Probability that a randomly selected student would have no opinion given their boy. So I'm going to start by looking at just my boys. So home in on just your boys. 55 total people. How many of those 55 had no opinion? 10. So of my 55, 10 had no opinion. And always reduce. 2 out of the way. Alright, let's look at it when there is a Venn diagram. A is a set of 10th graders, B is the number of high school students that have a computer. So I want the probability of A given B. So the probability of a 10th grader given that they have a computer. Well, I just want to focus on having a computer. So I'm going to look at just my B circle. So there are a total of 45 people in that. Oh, no, I lied to you. 45, 60 total people in that whole blue circle. I'm adding these together. Okay, now of those 60 people, how many are a part of A? 15, right? That's the only part that's going to allow circle A. If I'm looking at circle A, it only overlaps right there where the 15 is. So of those 16, 15 are 10th graders. And reduce it down to 1, 4. Now, if we did the opposite, so this time I'm asking for the probability of B given A, so the probability that they have a computer given their 10th grader. So this time I'm only focusing on my A circle. So I have a total of 35 people in my A circle. Of those 35, how many are also part of B? On the B circle. So right here, that overlap between my A and B circle. So 15 total are also part of B. And that reduces down to 3 others. Please answer any questions and add puzzle at the end of it.